Okay. So I was asking if my screen is visible, but my mic was off. That's fine. We can continue now. Okay.
Yeah,
So is
screen
my
is
screen
visible.
visible? Okay, good. So hello, everybody. I am Akshank Tyagi. Uh, I completed my Master of Science in the physics major at IISc this year. So I graduated just a few days ago, and I've started as a research associate in the CMB Cosmology group at Raman Research Institute. Okay, so last time we were able to discuss the expansion of the universe, and this time we will go deeper into it. We will look at the Friedman equations, and then we will look at the cosmic ingredients that make up our universe. Okay, so a small recap about lecture 1, if any of you have missed that. So we discussed that the whole universe is expanding. What that means, that observationally we see that the galaxies are moving away from each other, they are moving away from us, and it is explained in the terms of the expansion of space itself. The distance between the galaxies is increasing. The size of the universe is increasing rapidly. So as you can see in this video, maybe on the laser pointer. Yeah. So as you can see in the video, these galaxies, they remain at the same grid points of this sphere or the sphere's surface, but the distance between them seems to increase because the size of the sphere is increasing. So this is a good analogy for how the universe is expanding. The space between the galaxies is increasing, and this is what we call the Hubble expansion, right? And apart from that, if you remember, we also discussed that this is observed as cosmological redshift. So the light from distant galaxies seems to be redshifted. And that redshift, again, is happening because of this expansion. The wavelength of light is being expanded. Okay. So the wavelength of light increase as the universe expands, space expands, and the wavelength of light, which was emitted by the galaxy, and as it is traveling through the space, also expands. So the wavelength expands, and that causes the energy of this wave light to decrease, or causing it to redshift. And this increase in wavelength is denoted by Z. This is your cosmological redshift. Okay. So when we study distant objects, distant galaxies, quasars, supernovas, we always talk about this term Z, which represents how far away these are. And also, this is related to the scale factor. Scale factor of the universe is basically how much the universe is expanding. So this is your metric in a flat space-time, 4-dimensional. You have the time term and the 3 space dimensions, X, Y, Z. In an expanding space-time, only the space is expanding, first of all. Time, we leave it alone. So the space terms, the space dimensions X, Y, and Z are all expanding by A. Okay. So it's just a parameter which signifies how much the universe has expanded or is expanding. One important note is that yeah, A at t equals to present, right? So at present time, A is taken to be 1. Okay. So today's the scale factor today is 1, and in the past, t less than present, it would have been less than 1 because the universe was smaller. So the scale of the universe is smaller, and now it is increasing. So if today it is 1, in the past it would have been less than 1, and in the future it will increase above 1. Okay. Then we also discussed that looking far is also looking back in time. How? If you look at the sun, and the sun is 8 light minutes far, so you see the light that was emitted 8 minutes ago. Okay. Similarly, for the Orion Nebula, which is 1344 light years away, we see it as it was 1344 years ago. So the light emitted that we see today on Earth was emitted this many years ago. The same is also true for Andromeda. And so the light from Andromeda that we see was emitted 2 million years ago. So looking far is also looking ago. So what this means is when I talk about the redshift of a galaxy, it tells you the distance. It also tells you the time of the galaxy that you are looking at. Okay. So if I look at a redshift of say z equals to 2, I'm looking at a galaxy 3 billion years ago or something like that. So distance, time, and redshift are all related. Okay. Apart from that, we also discussed, very important, the shape of the universe. So this is known as the curvature problem. So we talked about a metric in a flat spacetime, which is this, right? Flat curvature. But you could also have positive curvature and negative curvature. How these actually come about is a part of general relativity. So I'll not go into too much detail of that. But these are the two solutions which are also possible and viable. That's why they are acceptable in the general relativity framework. And an important, very interesting fact is that you have all learned about the angle sum theory, that sum of internal angles of a triangle is equal to 180 degrees or pi radian. This is only true in a flat curvature or flat space. In positive curvature, the sum of these angles would be actually greater than 180 degrees. And in negative curvature, the sum of these angles would be less than 180 degrees. Here it would be greater than 180 degrees. Okay. Now, how these all of these things are related, how this redshift, how do you calculate the space's scale factor, all of these things are related using the Friedman equations. Okay. So this is the first Friedman equation, and this tells you something about the expansion rate. Okay. So as I told, expansion is measured by A, the scale factor. So A dot will be the expansion rate, right? Now, where does these Friedman equations come from? They come from Einstein's field equation. So basically GR. And if you add a ideal fluid situation. So I'll not go into too much detail of how these equations are derived, because for our purposes, for all intents and purposes of observational astronomy, we don't care. We know the universe's expansion can be modeled using these Friedman equations. Okay. So one important thing is this A dot by A that you see inside the parenthesis is known as the Hubble parameter. So you have H equals to A dot by A. Okay. So this represents how fast the universe is expanding. As I said, the expansion rate, right? And if you remember, there was something like H naught, your Hubble constant, right? This is the value of H at present time. So H is a function of time. It changes with time. And the present value of this Hubble parameter is called the Hubble constant. Okay. We'll discuss more about it later. But for now, that's it. Then you have some other terms like 8 pi g by 3, again, a constant. Then you have rho. Rho is the energy density. Okay. So, a few things. So, yeah, you remember E equals to mc squared? Right? So energy equals to mc squared. Einstein's famous mass and energy equality, right? Now here, whenever we write rho, rho is related to mass, but if I multiply it with c squared, this becomes your energy density. So this is your mass, rho is just mass density. Rho c squared is your energy density. Okay? But whenever I'm going to write the Friedman equations or any sort of equation, I will take c equals to 1. Okay, these are called your natural units, where c is 1, h bar is 1, and this makes life simpler. So rho is basically your energy density. Okay. So all the kinds of material that is there inside the universe, say matter, radiation, dark matter, all of these things have some mass or they have some energy, and that is accounted for in this energy density. Okay. Then what is the curvature of space? This comes here in this last term, k by a square. Okay. So if, as I showed you earlier, for a positive curvature, k is assumed to be 1. For negative curvature, k is assumed to be -1. Sorry. And for a flat curvature, k is supposed to be 0. Okay. So when you put -1, 0, or 1 in this first Friedman equation, you are able to calculate how the universe would expand if it had positive, flat, or negative curvature. Okay, good. So this is your first Friedman equation. Then you have the second Friedman equation, which relates the acceleration. Okay, so now you have a double dot. So you had you have a dot in the first Friedman equation, and you have a double dot in the second Friedman equation. And again, this is related to the energy density as well as the pressure. Okay, pressure from each of these components. Whatever is giving you this total energy density, they will also have some pressure, and that is also needs to be accounted for, because you want to see how fast the expansion is going. Okay. Okay. Then is this. Also, one important thing to note here is this minus sign, right? So that would mean that a double dot is negative, right? What does a double dot being negative means? You all have studied, right? In kinematics. What does x double dot being less than 0 mean? Anybody?
Decelerating.
Correct. So a double dot less than 0 means deceleration, right? So this would mean that the universe's expansion is decelerating. Okay. Why? Because this equation has a negative term. Because energy density cannot be negative, the pressure cannot be negative. This right-hand side is negative. So it would seem, okay. Oh, wait, there should be a double C here. Single N. Don't mind my spellings, guys. I'm bad at spellings. Okay, so as I was saying, a double dot seems to be negative. And that would mean that the expansion of the universe is slowing down. Okay. From this equation, because a double dot is negative. But when we were able to measure this expansion. So remember the Hubble law, as I said, H naught, your Hubble parameter, measuring how fast these galaxies are moving, their velocity of their recession velocity, VR, with respect to the distance to these galaxies. You have velocity here and the distance on the x-axis. So velocity versus distance should be a straight line. That is your Hubble-Lemaître law. There is my cursor. Yeah, here. V are directly proportional to D. Right? And so this was measured first time by Hubble in 1929. He used Cepheids. Okay, so what he used were Cepheid stars, Cepheid variable stars. Okay, but today we can use supernovas, and that allows us to go much deeper, to much larger distances, to much higher redshifts. Today we have supernova data of up to 10 redshift. Okay, so 700 megaparsec is around 2 or 3. I think 2 megaparsec. Sorry, z equals to 2. Okay, but today we have data for up to z 10. Okay, redshift data from supernovas. Okay, now this was interesting. This was measured, and this supernova data came very recently. So the first time we were able to measure distances using these type 1A supernovas was 1998. Okay, so very, very recent. I don't think any one of you would have been born, but yeah. So some of your brothers or elder siblings would have been born maybe by this time. So these discoveries were made quite fairly recently, uh, assuming that Hubble expansion was discovered 100 years ago, right? Okay. So one thing,
Can you
important
tell
thing,
what is hello?
yeah, yeah.
Yeah, like can you tell what is seed variable stars?
Okay, okay, good. So basically, what is a variable star? Oh, back. Yeah. So a variable star is something whose brightness changes with time. Okay. This is your variable star. Very simple. Brightness changes with T. For Cepheids, what happens is the brightness almost follows a sinusoidal pattern. Okay. So the star gets bright first, then it gets dim, then again it gets bright. And so you are able to measure this wavelength, sorry, this time period between these two peaks. Okay, so this is known as the time period. How can I? That's fine. So you have the time period between two peaks, and this is directly proportional to the luminosity or how bright the Cepheid should be. Okay. Now, because you know the luminosity of this Cepheid now, you can easily observe this time period. That allows you to calculate what will be the luminosity. This is known as Leavitt's law. Okay. So it relates time period of a Cepheid to the luminosity of the Cepheid. Okay. And then from the luminosity, you can calculate the distance because you know how bright it appears to you and you know how much bright uh, it is near the star because from the luminosity. So that allows you to calculate the distance. Okay. Something similar is done for supernova. What supernovas? Supernova type 1A. Okay. So there are many types of supernovas. You have type 2A. It's happening. You have supernovas of type 2A, 2B, 2C. Okay. So you have different kinds of supernovas depending on their properties. So it's mainly spectral properties, or also wait, it should be type 2A. I am sorry. No, I'm okay. What am I doing? This is type 1A only. Okay. So this is type 1A supernova, which is used as a standard candle. Okay. What does standard candle mean? So just like the Cepheid variable, you can calculate how bright or how luminous that type 1A supernova is. And from that, you can calculate how far away that object is. Okay. What actually is a type 1A supernova? It is a white dwarf around a massive star. Okay. Or a red giant. So that white dwarf accumulates gases or matter uh, from the neighboring star, and then it is able to increase its mass. This is a white dwarf at the center. So it's a binary star system. You have a white dwarf and another red giant. Matter from red giant is falling onto the white dwarf. And once the white dwarf reaches a limit known as the Chandrasekhar limit, I should write it up here. When it reaches Chandrasekhar limit, which is about 1.4 solar masses. Okay, so 1.4 into the mass of the sun. That is called your Chandrasekhar limit. What happens? The whole white dwarf explodes. Okay, and that explosion is known as a type 1A supernova. Now, because this mass limit is so well known, that this explosion, this type 1A supernova is happening at this exact mass range of 1.4 solar masses, you can calculate how luminous the supernova is. Okay. And once you know the luminosity or how much energy the supernova is giving out, you can calculate how distant away it is from us. Okay. So you can calculate the distance. And this y-axis velocity comes from the redshift. Okay. So you already have the redshift data, or you can even get it from the same supernova as well. Okay. So you are able to plot redshift versus distance. And that gives you this, again, straight line of the Hubble law. Okay. To much larger distances. Now, this was fine. But what actually is observed is that when you plot A dot, okay, so now you're plotting the Hubble parameter divided by 1 plus Z, which is A dot. Okay. So if you plot A dot with redshift Z, what do you see? So again, Z equals to 0 is present. Okay. So this is past. Time is moving this way. Okay. So you see the redshift is increasing to your right on this graph. So what you are seeing is the universe, or the A dot, is actually increasing at the present time. A dot here is increasing. So first it was decreasing, right? A dot was decreasing, and now A dot is increasing. So Z equals to 0 is present time. And the supernova data tells you that the A dot is increasing, right? But why is that surprising? If A dot is increasing, that means A double dot is greater than 0. But your first Friedman equation, the second Friedman equation uh, wants A double dot to be negative, right? As I told you earlier, and this comes from very fundamental principles. So high chances, very low chances of this being wrong. But what we see, A double dot should have been negative. Observationally, it has been observed in 1998 for the first time that A double dot is actually positive. So the universe's expansion is accelerating. Okay. This A double dot should be positive. How do we make that positive? We add an extra term here at the end. Okay. Now this extra term is called the cosmological constant. This lambda, capital lambda, is called the cosmological constant or your dark energy. Okay. So the rest of the equation remains the same. But because this whole thing is observed to be positive, you add a positive term plus capital lambda. Okay. Which is overpowering this negative term. This whole thing is greater than this. Sorry. So this positive term is greater. And so A double dot is positive. Okay. This was added observationally. Now there is also a very interesting story about it, that when Einstein gave his general theory of relativity and then used it in cosmology, he introduced this term himself. Okay. He gave this term, but not for an accelerating universe. He actually wanted to go this to zero. He wanted the universe to be static. Okay. And so he said, this should be negative there, and there should be some extra term, which is causing this whole term to go to zero. Okay. That is what Einstein wanted. But alas, he was wrong. And we observed, and Hubble observed that the universe was expanding. So this term was dropped out from the first Friedman equation. But today we know that A double dot is positive, and so this term is reintroduced. And this is called your dark energy. Okay. So this is your most important proof for dark energy, that we see that the universe's expansion is accelerating, and which can only be caused by a positive term. And that positive term is what we call dark energy. Okay. Now, what actually is causing this dark energy, we don't know, but we'll discuss about it a little later. Okay. So the rest of the terms we already discussed. The only new term is this lambda. Then you also have the same term added in the first Friedman equation. Okay. Lambda by 3. So you go and add this all the way back into the Einstein's field equation. Okay, that's where Einstein had introduced it. And from there, you generate these first and second Friedman equations, which gives you these lambda terms, lambda by 3. Okay. Again, some books will show this is lambda c squared by 3. I don't care. As I said, c is 1. Okay. So you just put c to 1. And these are
Like,
your actual, yeah.
excuse me, like there is a question in chat. Like, should I read it out or like, do
Yeah,
you
yeah.
want to read it?
You can read.
So, like, it's a question from Vadika. Uh, if we are just adding something to the equation to make it positive,
Yeah.
undefined, we call dark energy. Why divide by 3? Why not just write the constant by itself?
Okay. So this division by 3, we didn't. So what I did was a small mistake here in saying that we actually added this term here. So as I'm telling you right now, the term is actually added in the Einstein field equation. There it is added just as a simple lambda. Okay. From there, when you derive these Friedman equations back, you get lambda by 3 here. Okay. You get this lambda also can be expanded in terms of G and stuff like that. GC squared. But we don't care. So this lambda by 3 actually comes when you rederive it. So the Dark energy is actually added up into the Einstein field equations. And then when you derive these Friedman equations back, that's where gets you this 1/3 factor. Okay. Okay. Moving on. So
Wait,
now, yeah. Okay.
so here we are taking lambda as a constant or as a variable with time.
So very good. So this lambda, as I said, the name suggests this is cosmological constant. Okay. So it is a constant. It does not change with time. So this is called your lambda CDM theory or your standard model of cosmology. Okay. Here you have lambda, which represents the cosmological constant. So this is a constant value. It has not changed with time. It does not change with redshift. Okay. So it has been constant throughout the universe, throughout the history of the universe. And then the CDM is cold dark matter, which we'll come to later. Okay. So for now, this lambda is a constant term, which is called cosmological constant, and it has been added to make this equation positive, as we see observationally. Okay. Now, the current theories, the leading theories actually say that this lambda is changing. Okay. I'll not go into those. So those are called scalar dark energy theories. So recent data from DESI suggests that scalar dark energy theories where this is not a constant, this whole term, and it changes with the history of universe, those seem to be much better fit for the data that we observe. Okay. But for today's lecture, we'll only deal with the cosmological constant. Okay. Any other questions? Okay, so moving on, the next thing to discuss is your third Friedman equation. Now, most people actually don't call it the third Friedman equation, but yeah, what so it's derived a little differently. But again, it's very important to study the constituents of the universe. So it tells you the density derivative, the derivative of the density, how it is related to the scale factor. Okay. So you have all of these different constituents. How will their density change as the universe expands? So now how do you solve this? So we know that pressure and density are generally related. Okay, for any kind of material, whether it is matter, whether it is radiation or anything else, pressure and radiation are generally related. Okay, sorry for that, guys. My laptop seems to have overheated and it got disconnected. No worries, I'm back. Share my screen again. Is my screen visible?
Yes, it is.
Okay. Okay, so yeah, repeating what I said earlier, if I had gotten disconnected, you missed any of it. This is your lambda CDM model, where this lambda is called the cosmological constant, which does not change with time. Okay. Why did we have to introduce this? Because we observationally saw that this whole term should have been greater than 0. Okay. And next, you have the third Friedman equation, which relates this density of any constituent with the scale factor. Okay. And it requires the density of that constituent and the pressure. Now, pressure and density can be related. This is called the equation of state. Many of you must have studied this in, if you take a condensed matter physics course, or you take EMT when you study light, then you obtain this kind of relation, right? Now, if I use this P equals to W rho here, you can solve this equation simply to obtain this equation. Okay. And this is much simpler to understand than the previous one. So we will use this. What it tells you, that the density of any constituent is dependent on the scale factor in this manner. And it depends on the equation of state W, or the equation parameter of state W. Okay. Now, you all must have seen this pie chart in some form or the other. Okay. These are your cosmic constituents, or as I like to call them, cosmic ingredients. Right? You have your normal matter. So all that you see around you, all matter that is present in the galaxy that you see, that is visible to you, is normal matter. Okay. But it's only less than 5% of the entire universe's energy. Okay. So this is your mass energy, basically energy pie chart. Okay. Energy budget of the universe. So you have only less than 5% of universe's energy and mass is in the form of visible matter that we understand. Okay. So you must have read about the standard model of particle physics, right? You have quarks, you have electrons, positrons, you have neutrinos, and you have bosons, right? So these quarks make up your protons, neutrons, and so all matter that we understand, or that particle physics understands, is visible matter. Okay. Rest 95% of it, we don't truly understand. Okay. Rest of it, 25% or about, is called your dark matter. Why is it dark? Because it is invisible to us. Okay. Invisible matter. So I know the name is quite on the dot, but dark here simply means that you cannot observe that matter. What it is invisible to your eyes. That means it does not uh, emit light. Okay. Cross does not emit light. Visible matter does emit light. It does have interactions with photons, but dark matter does not. That's why it is dark. That's why it is invisible to us. And then the rest or else of the 68% or 69% of the energy of the universe is your dark energy. And as I said, we will assume dark energy to be lambda, the cosmological constant. Okay, good. Then, but when we study cosmic ingredients, you have, as I said, matter and dark energy. One thing which is not visible here in this energy pie chart is your radiation. Okay. And what is radiation? It means all relativistic particles. All particles which are moving close to the speed of light. Relativistic means their velocity is closer to the speed of light. What does that include? Photons, neutrinos, maybe even cosmic rays. Okay. So these are all your relativistic particles. Now, important thing to remember is this energy pie chart is dependent on present day, is defined for present day. So in the present or current universe, this is how the energy density looks like. But in the past, this could have been very, very different. And it was. Okay. So radiation is actually still present, right? We know radiation is there. You have light all around you. Sun emits light. You have light from the cosmic microwave background or light from Big Bang. Then you have light from coming out of your tube light or your light bulb. So light is there, radiation is there, and it has some energy. But in the present day, that energy is almost 0.0001 percent. If it is in percent, then there's a less zero. But yeah, you understand my point. So radiation is still there, but it makes up very little of this cosmic pie chart today. In the past, it made a significant contribution here, but let's see why it does not today. Okay, so you have three main cosmic ingredients. You have radiation, matter, which is both this normal or baryonic matter, and the dark matter. And then you have the third, dark energy. So again, you have this equation for density, and for matter, W equals to 0. What does that mean? That pressure is almost 0. Matter exerts no pressure. Has no pressure. Got it? So, again, but you must have heard that water, right? We have like studied that water emits some pressure, right? Then are we wrong in saying that uh, matter does not have any pressure? What do you think? Okay, so what is the reason for this pressure? Can anybody tell me? What is the reason for
Radiation?
hydro? Huh?
कुछ नहीं भाई.
Okay. Anybody else? What is the reason for hydrostatic pressure?
Gravity.
Correct. The reason is gravity. Okay. If there was no gravity, there would be no hydrostatic pressure. Got it? There would have still been a very minuscule pressure, but again, as we said, it's close to zero, negligible. Okay. And that's why we assume all matter inside the universe to be dust. Dust means it has zero pressure. Okay. Unless it has some other external force acting on it. If you have gravity, then it might cause some pressure, similar to water. Okay. So when you put W equals to 0 here, things are simplified, and raw matter is dependent on A raised to the power minus 3. Okay. Which makes sense. Because if you have a small box and then the box increased in size, okay, so the side was say 1 and today it is A, and how much did the volume increase? Guys?
A cube.
A cube.
Correct. Volume is A cubed, and so density would be inverse, right? So the amount of matter inside remained the same, but the volume increased, right? And it makes sense that there was matter inside the universe is expanding, the volume is increasing, and so the total matter energy density should be decreasing. Okay. But what you see, the amount of matter inside the small cube and the large cube remained the same. So what it means is your matter energy is conserved with time. The total amount of energy that is contained within matter remained constant. Okay. Or it is conserved with time. So this is your normal energy conservation law. Okay. What is not conserved is the energy density, but the total energy is conserved. Okay, good. Next, we move on to radiation. Now, some of you would have read that there is something known as radiation pressure, and which is 1/3 of radiation density, right? And this is your equation of state. So your W equals to 1/3, right? Now, if you use this W equals to 1/3 here, that simplifies and you get pressure is P rho by 3 and radiation pressure, radiation energy density is decreasing A raised to the power 4. Okay. Now here we saw energy density of matter was decreasing as A cubed. Here it is decreasing for radiation as A raised to the power 4. Okay. Why is that happening? Because if you remember, expansion of the universe is causing redshift. That redshift is basically expanding this wavelength, right? So you have Hubble expansion, which is expanding the wavelength of the light, wavelength of this radiation or the relativistic particles. Their wavelength is increasing as the space is also expanding. And because of that, the energy of these particles is decreasing. This is essentially what is redshift. The energy is decreasing, so it is becoming redder. Okay. And how much does the energy decrease? It decreases by a factor of A or scale factor. Okay. Should pick the different day. No problem. Yeah. Yeah. So you have similar to matter, the cube is increasing in size. So the volume change was A cubed. And so there will be a cube change from here in density. But the energy is also decreasing as 1 by A because of this redshift and because of this expansion. And so the total radiation energy density decreases as A raised to the power 4. Now, what is interesting here is that this energy is actually being lost to space. As space is expanding, the wavelength is increasing. So the energy of the radiation which was there, that has lost, that has been reduced. And where has this energy gone to? Simply into space. Okay. But this breaks your conservation of energy. Right? You all have studied energy cannot be created or destroyed in your high school classes. But this is not true when it comes to cosmology. Okay. So no global, wait, I should change the color. No global energy conservation. Got it? So energy is not conserved when you talk on very, very large scales, the scales of the universe. Because energy is being lost by radiation. Okay. Next, if you do the same thing for cosmological constant lambda, for lambda, we assume this W to be -1. Okay. Again, this property comes from how we introduce this lambda into the Einstein field equation or GR. But it's quite clear that W should be -1 for this cosmological constant. Okay. Now, it's straightforward. Put W equals to -1. That would mean your density is constant. Right? Density is constant, does not change with scale factor. But what this means, again, very interesting and important, is that if the size of universe increases, the amount of dark energy is also increasing. If you had just 3 here and it increased, now the dark energy has increased. Okay. Why? Because the energy per unit, yeah, the energy per unit cube remains same. The density remains same. Right? But in total, as the universe is expanding, so that means energy is being created. Dark energy is increasing with time. Okay, the density is constant, but the total dark energy content in the universe is increasing. So as the universe expands, dark energy expands with it. Okay, dark energy increases with it. Where does the dark energy come from? We don't actually understand. Some people believe that it is coming from quantum fluctuations of vacuum, and that's why they call it vacuum energy. So it becomes a specific property of the vacuum itself, property of the space itself. So if you increase space, if you increase the vacuum, you are generating this kind of energy. Okay. But this is also something we are not sure of, what this dark energy is coming from. This is fine. So what this means is that we saw radiation is decreasing A raised to the power 4. Matter density is decreasing as A cubed. And dark energy density is constant. So when you look at these densities of these constituents with the scale factor A, what you see is that in the past, so this is your present. Okay. This here, this point is z equals to 0 or close to 0. Okay. So this is your present and this is your past. So what is happening is we know the current radiation density. This is your radiation density, this is your matter density, and this is your dark energy density. Right? These are current. So I'm not radio, no, whatever. And this is the this is what is represented in that pie chart. That 20 around 32% is matter, rest is dark energy, and as you can see, radiation is much less than both of them. Okay. And now we know how these scaled back in time. As the universe was smaller, we simulate how these densities changed. So you see this first dot here. This first dot is your dark energy and matter equality. At this point, at this redshift, which is around 1.2, at this redshift, oh sorry, it is 0.2. 1 plus z is 1.2, z is 0.2. At that redshift, the universe was 50% dark energy and 50% matter. Okay. If you go before it, it was much higher matter than dark energy. And at some point here, there was the matter radiation equality. Okay. And at this point, radiation was the dominant uh, constituent of the universe. So almost 100% of the universe was radiation. All else, very little matter and dark energy was negligible. But as the universe is expanding, so what is happening is radiation is decreasing super fast. Laser? Yeah. So radiation is decreasing a raised to the power 4, and so the slope is much steeper. The radiation density is dropping very, very fast. Matter is dropping more slowly. It's a raised to the power minus 3. And so at some point, matter was able to overthrow the amount of radiation in the universe. And after that point, matter became the dominant force. So these are called your eras. This is your radiation dominated era, where radiation was, yeah, all of this part. Sorry. Before this redshift, all the universe was radiation dominated. Radiation was the uh, largest constituent. And between this redshift and this redshift, you have your matter dominated era. Okay. Where matter was the dominating force or the dominating constituent. And today, dark energy, as we know, is the dominant era, dominating constituent. So we are today in a dark energy dominated universe. Okay. Now it is important to know what uh, constituent is the more dominant one, because that dictates how the universe behaves. Okay. Because in the past, when radiation was more dominant, as I said, radiation has some pressure. right? So the radiation was pushing away everything. It was pushing away matter. It was pushing away all kinds of particles. And because there was so much radiation, it was generating new particles uh, spontaneously. Then at some point, matter became the dominant force and radiation started to free flow through the universe. Okay. And today, dark energy is the universe, which is dark energy is the dominant force, which is causing the universe expansion to accelerate. So during radiation domination and matter domination, A double dot was negative. Okay. Or less than zero. Only in the dark energy dominated era, A double dot is positive. Okay. This matter.
Uh, by this,
Yeah.
can we say that the expansion rate is dependent on the amount of radiation present in the universe?
Not just the radiation, matter, and dark energy. So basically all the constituents. Okay.
No, like
So
you
that
said that the radiation energy is consumed by the universe to expand itself.
no, that's a misconception. Radiation energy is not being consumed to expand. The expansion is being caused by dark energy. The radiation is losing its energy, which is completely separate. Okay. This energy
Okay.
loss of radiation is much different than what is this increase in energy from dark energy. Okay.
Hmm.
So I used to think the same way as you are thinking, that if the energy is being lost by radiation, why is not that explaining the expansion of the universe, right? But the problem is, you see the density of radiation, it's so low. At present time, the density of radiation is so low that you can't explain the observed acceleration from this energy lost by this. Okay. And you see the energy density of dark energy is much higher. So it can't really explain that, the observed value. Otherwise, it would have been a good solution. Okay. So that could only have been possible when this crossover happened between dark energy and radiation. But today, it's definitely not possible to explain whatever we observe through radiation energy decreasing. And so, what these Friedman equations are telling you, as I said earlier, that the expansion rate of the universe and the acceleration of the universe depends on the constituents. Okay. Either those constituents are here in form of radiation or matter, or it is the cosmological constant or dark energy. Same for the expansion rate, whatever component is here. But here it's also dependent on this uh, scale, sorry, curvature of the universe. Okay. Any questions so far? See if there are any questions in the chat. Chinmay would have told me otherwise if there were. That's fine. So no questions, guys?
Like there was a question, like there was a discussion long while.
Okay.
Like Sarthak wanted to ask, like, how is gravity related? When you mentioned uh, when matter has, uh, like you mentioned those density terms for matter, right? So you
Yes.
mentioned gravity there, and he wants to know how gravity is related or something like
So
that.
gravity is not exactly related here. Uh, why can't I move this?
No, like you said, the pressure by the visible matter.
Yeah. So gravity is related to the pressure. Okay. If you have gravity, so what is pressure? Pressure is just force upon area, right? When you are standing up on the surface of Earth, okay, you are standing here on the surface of Earth and it's not working there, but that's fine. What is happening? You are being pulled down by this force of gravity. And that is the pressure you are causing on Earth, right? If there was no gravity, there would have been no normal force here, right? No reactive and opposite normal forces. And so there would be no pressure. As simple as that. You would just be freely floating. There might be some pressure because of cohesive forces. But again, as I said, not just gravity, all other forces. So if there are no external forces on matter, it behaves as a pressureless fluid. Not fluid. That's what we assume in generating these Friedman equations. Okay. So if you remove any external forces, you would have no kind of pressure. Any other questions?
In
So what
the
do you mean by
Friedman,
energy?
Okay. Who is speaking? Let's see. Yeah, guys. You can ask your question now.
okay.
Hello. Yeah.
In the Friedman equation, the pressure term which like we are talking about pressure on what or pressure due to which force? Like the pressure is related to what? I'm not able to understand that.
So take for example radiation, right? You have studied radiation pressure, right, Idris? So
Yes,
if
yes.
you have a surface and you have light, right? And this is producing photons which are hitting this surface. Okay.
Yes.
Now, because you know these photons are moving with some velocity, we know that velocity is c, right? That means they have some momentum. What is the momentum of radiation? Guys, remember?
E by C. No.
Correct. E by c, right? That's the momentum of radiation. Now, when this radiation hits and it reflects, it is causing some change in momentum, right?
Right, right.
So because of this change in momentum, it is causing a pressure. Okay, that is unfortunate. Yeah, that they are both P's. Let's keep it small p. Yeah. So when you are talking about two surfaces, right? If you have, let's say, a matter and another matter surface, what it means is there won't be any pressure in between them in general. But if you have matter with radiation, you would have pressure. If you have radiation on radiation, you would still have pressure. Okay.
Okay, so when we are talking about the visible matter, so in that
Yes.
case, uh, like, in that case, what is the pressure? Like here, it is the radiation pressure, right? So
Yes.
radiation pressure somewhat makes sense, but when we are, what is like matter pressure, like I'm not able to understand that.
That's
What
the whole
pressure are,
point. That's why matter pressure is zero.
okay, okay.
So similar to, that's why I gave you the example of water. Matter can exert pressure on things. It can exert pressure on surfaces, but only when there are external forces present. If you have two blocks of matter without any external force, okay, assume these are two blocks of metal just floating in the universe. Do you think they will have some pressure? They will have some forces in between them, except gravity. And gravity, they will be being pulled up towards each other. But yeah, there is no inherent pressure between these two objects. Okay, that if there is
Yes.
pressure, that happens because there is some force that is pulling them together or whatever. Okay, either it is the electromagnetic force or the gravitational force that will cause some pressure. But naturally, these matter particles will not exert pressure on each other. But if they were moving, say for example, you had something moving this side and this matter moving this side, then they would have collided and this collision would have caused pressure. Okay, that would have been a whatever, and either an elastic collision or an inelastic collision, but there would have been some momentum transfer, and that momentum transfer would have been your pressure, right? But when you are talking on such large scales, it becomes that's why it's an assumption that matter is not moving, and that's why it's not exerting any kind of pressure. You have pressure from particles, but we are neglecting all of that. Okay.
Yeah. Okay.
Okay. Any other questions?
Yeah, there is also a question in chat if you want to read it.
Yeah, you can just read it.
Uh, okay. So, like, I'll just read it out. If general relativity treats gravity not as a traditional pulling force, but as the curvature of space-time, how does
Okay.
gravity physically cause matter particles to converge and increase in density? How does this geometric view of gravity interact with the physical kinetic pressure of particles on a cosmological scale?
Okay. That can you repeat the
Yeah.
first part of the question again?
Uh, yeah. So like, uh, it says if general relativity does not treat gravity as a pulling force, why does
Yeah.
curvature cause particles to come together
Okay.
and increase in density?
Okay. So we have space somewhere. Yeah. Let's use this space. There is no space. Okay. So now again, this is a question from general relativity. It's not from cosmology, but I'll still try to explain to my best understanding. So if you assume the universe to be a stretched fabric, right? You all must have seen this demonstration. And you put some sort of matter here, right? And this causes the space-time fabric to be curved, right? Let's change color. So if you have any kind of matter particle, it is in this space-time well, sort of. What happened? Yeah. It's in this space-time well. When you have another particle, what will it do? It will create its own well, right? That is what is happening. Let's say this is your sun and this is Earth here. So Earth has a smaller potential or space-time where the space-time is being curved towards it. Again, this is a two-dimensional picture. what is happening actually is three-dimensional curvature of space-time. And there is no way of doing that unless I can draw in 4 dimensions. So we'll stick to this analogy. So what happens? This is fine. This smaller well and this larger well. Their net effect, if you look at from far away, is that there is some pull between them. What that means is there is a total curvature. Okay. This is caused by the sum of these two masses. Okay. And that is slightly offset from this main bigger potential well. And that is why it wants to so you have heard that GR tells that matter bends space-time, right? What you have not heard is the second statement that all particles, all objects, all matter, radiation, whatever, travels in a geodesic or a straight line. Okay. So when you calculate the geodesic for this Earth or for any object in this space-time well, it comes out to be moving downwards. Okay, so that is the thing. So this is basically how it's explained, that all particles must move along the geodesic, and that geodesic is defined by the curvature of spacetime. So matter is curving spacetime, that curvature is causing a new geodesic, and that particle tries to move along that geodesic. Now, if it had a circular velocity, it would be able to move along this geodesic, right? This is also a geodesic path, and that is basically Earth's orbit around the sun. If there was no this horizontal velocity, then it would follow this geodesic, which is moving downwards, or in reality, moving towards the sun. Okay. So that's the answer to your first question. The second, how does gravity act on such large scales, is directly is what these Friedman equations are. Okay. So this total, if you look at this first point only, and you forget the curvature and you forget the lambda, what you see, matter will tell you how the universe is expanding or how the universe is slowing down. Okay. The same thing in the top. The universe will slow down if there is only matter, and the universe expansion rate will increase. Wait, what did I just say? Yeah. So the expand A dot will decrease. That's why A double dot is negative. That's fine. How that will happen will depend on this matter. Why can matter affect A dot? This is simply gravity. Okay. This is simply the how the universe is the total, what do we say, space-time fabric. If there was no matter or anything inside the universe, it would expand freely, right? A would be independent of everything. But because there is some matter, and that is causing this curvature in space-time, right? This is causing this expansion of this universe to change. This is not the same as it would have been when A was independent. If there is matter, A would be dependent on the matter, dependent on rho, right? Because this matter, just by its virtue of existing, is causing the curvature of this space-time, and that will tell you, that will change the way the space-time should expand. Okay. Some people like to say that simply because matter is there, it is slowing down the expansion of the universe because gravity is pulling things together. That is the wrong way of thinking about it. because gravity is not pulling space, right? Gravity, matter is only pulling matter. Matter is not pulling space. What is actually happening? Because of the curvature being caused by these matter or radiation particles or whatever, that is causing the expansion to slow down if there is matter. Okay. So does that explain? Whoever had the written question?
Yeah, it does.
Okay. Okay. I think it's been quite late. And if let's cover one last topic, then I'll leave you guys to go have dinner. This is the last topic for today. And it's simply, we go back to the first Friedman equation. You had Hubble parameter h, right, which is the function of time t. Now you can calculate this Hubble parameter using today the h naught today and the radiation matter density, curvature density, and the dark energy density. What are these things? These are called relative densities. Relative density is omega. What it means, omega I is basically rho I divided by rho critical. Okay. Rho critical is when k is 0. Okay. So if I put k equals to 0 here at present time, a will be 1 and this will be h naught. Lambda also is a constant. So that gives you what is the value of this rho c. Okay, this is called the critical density. And this is the amount of energy density required such that the universe is flat. Okay. Now, the important shocking fact is we have observed that the universe is flat. We have been able to measure. There are ways to measure this k. How? We simply write 1 equals to omega m plus omega r plus omega lambda plus omega k. Right? And so we are able to measure all these three things. And then we can infer what should be omega k. And what we have inferred is that this whole thing goes to 0. That means k is going to 0, space is flat, or space-time is flat. Okay, very important. This is so important and so accurately known that the space is flat that it has become a huge problem. So as I said, Einstein's theory would have accepted a spherical universe, an open universe, and a flat universe. But why is the universe flat? Even though there is some matter inside it and some density which would have caused it to curve, is a huge mystery. Okay. And people theorized something called the inflation. No, wait. Yeah. People have theorized an early expansion of the universe called the inflation to cause k to go to 0. Okay. So this is all for today. And yeah, so coming back to this formula, you can calculate what was the Hubble parameter at some redshift if you know the omega lambda, omega k, omega m, and omega r. And they are all scaling by the scale factor that we already saw. Remember, radiation was a raised to the power minus 4, matter is a raised to the power minus 3, omega lambda was constant, and K is a raised to the power minus 2, as you can see in the first Friedman equation. But what we observe today from the data observationally is that omega K is 0. So K is also 0. The universe is flat. Okay. Any other questions from this? If not, that's it for today's lecture.
Yeah, there is one more question on the chat.
Yeah.
From Vadika, how come the expansion of universe and moving of galaxies indicate a spherical universe, but apparently k equals 0?
Okay. So your second half of the question I could not hear properly. Can you repeat?
How come the expansion of universe and moving of galaxies indicate a spherical universe, but apparently it's been proven k equals 0?
Okay. So the first part of the question is technically wrong. Like the movement of galaxies does not say that the universe is spherical. Okay. If you might be confusing it because of the video I had shown earlier, right? The expansion of the universe, that was just an analogy. Okay. The universe is not actually spherical. The observable universe around you is spherical because you can see up to a certain distance in all the directions. So you have a sphere around you, but that's not the whole universe. The whole universe is much larger than the observable universe. And here we are talking about this curvature of that whole universe. Okay. I know it is slightly non-intuitive about what this curvature is or what this shape of the universe is. I did try to explain it a little bit in last lecture, so maybe you can give it a look. But yes, as I was saying, the universe is expanding, but that also suggests the universe is expanding in such a way that suggests that the space-time is flat. If it was not flat, it would have been expanding in some other way. So as I said, I showed you the graph between A dot and Z, right? That graph itself shows that K should be 0 and K is close to 0. Okay. Any other questions?
So I had one, like you showed that pie chart for like a percentage of visible matter, and dark energy, right?
Yeah.
So, like, how do we know those proportions? Like, how did you calculate it?
Okay. That is a very interesting question. And if I had prepared those slides, I would have shown you. So that comes from CMB. So this result is from the measurement of CMB. So CMB, as you might know, is called the cosmic microwave background. It's something that I work on personally. And it's the radiation from the early universe that we can see today, right? So you have something known as the power spectrum of this CMB. So hopefully if we have the third lecture, then I'll discuss CMB and all of other topics. So you have this is sort of a power spectrum that you observe. Okay. You have some of the small peaks. This is called the power spectrum or CL. Now these peaks that you see, these are known as acoustic peaks. And these peaks are dependent on how these matter and dark energy density. Oh, wait, I should have that screen already open. Wait. Yes, good question. I did have that open. Let's see. Store. Yes. So this on the right that you see, this is the CMB which is observed. Okay. So this upper right corner is what is actually observed by the Planck mission. Okay, Planck is a space satellite that had observed CMB in 2010s. Okay, now when I change, you have the three sliders: normal matter, baryonic matter, dark matter, and dark energy. Now you look at these spots, how these spots change when I move these sliders, right? You can see this dark energy changing, then dark matter. And you can clearly see that there is difference. It is making a difference when you change all these parameters, right? It looks nothing like our universe. But if I go to what is the percentages that I already told you, guys, you remember the pie chart? Tell me, how much was normal matter? What percentage?
4, I think.
Yeah, it is around 4 to 5%. So 0.05. Okay, then dark matter was? Dark matter was around 28%. Yeah. 27. Yeah, let's keep it there. And then rest of it is dark energy. So around 68%. See, you see that it has matched, right? So because we know how these spots should look like on the CMB, since the early universe is so well understood in some terms, so we know how these spots should look like. These are called the CMB anisotropies. Okay. And you see, if it's even given universe similarity 100%. That's good. Yeah. So we were able to match it. And so this shows you how these energy densities can be calculated using the CMB. So from the CMB anisotropies. Got it? And these results that I showed you, these are from Planck 2015 result. Okay. So every time a new CMB paper comes out, they change them slightly, but roughly these are the correct values. Okay. Any other questions?
Means can you share some resource or something which we can read upon to like follow with the lectures?
With the lectures,
Like
okay. I have
like
one
with the
very good source. So if something simple, okay, I'll share it in the chat. Will you be guys able to access this chat after this meeting is over?
Yes, I think, or
I
else
think so, right?
we'll
Let me.
shift that.
Okay, so I'll stop sharing my screen and I will find that paper out. Should have it somewhere. Yeah, found it. So this is a review paper by V.A. Rubakov. It's quite good. Otherwise, you can read the book by Scott Rudelson. So both of these are good resources when you are starting with cosmology. The paper is a little bit more general and much simpler to understand, I would say. Okay, any other questions?
Think not. Uh, I think we can end now.
Okay.
Okay,
Thank
Idris
then
is
you.
we
typing something.
oh,
Yeah, let's wait
Thank
for
you.
him. Oh, okay. Yeah,
yeah,
thank you for
thanks a
inviting me.
lot. No, thanks a lot for this wonderful talk. Yeah, thank you from Astrae.
Okay, you're welcome. Yeah. Happy to always like discuss and inseminate, because even I get to learn new things and ideas. Okay. Thank you so much,
Okay
guys.
then. Yeah.